So now we're going to talk about group comparison. And as we've seen in previous modules, we can compare two groups with each other and compare their averages. This is known as a t-test. However, sometimes we want to actually compare multiple groups at the same time, 3, 4, or 5 groups. Take, for example, comparing scores between 3 classes. We'd want to compare the average score in one class versus the second class versus the third class to see if there's a statistical difference. If it is, we can then investigate why that's the case. Other examples include comparing the average customer order between Group 1 and Group 2, which could be Store 1 and Store 2. We also might want to compare the average number of clicks between 3 different versions of a web page. In that case, we're going to determine whether or not the web page actually has a difference that we want to explore. And as we said before, we can compare the average grade between multiple classes. So these are known as group level comparisons. And our goal is to determine whether the means are statistically different from each other. So it's really important to understand why we're doing what we're doing. We're going to compare 2 or more groups and determine whether one is statistically different than the other. Now let's review the t-test. The t-test is a basic test that allowed us to compare 2 groups and compare their means. Now, what's interesting here is we have an example. Let's say we have a sample distribution that is normal. This comes from human temperature, with a mean of 98.6 and a standard deviation of 0.9. If 2 groups are the same, then I should be able to take another plot that looks like this, and they should overlay with each other. Now, they won't be perfectly overlaid on each other. They might be shifted a little bit to the left or to the right, but statistically, we're going to determine if the means could statistically be within each other's boundary. Remember, we call that a confidence interval. And the statistical measure, the t-test, is actually going to tell us the probability that the means are the same. Now, we saw how to use the t-test in the previous module, but let's review why this works. When we compare 2 means, we take the sample mean of x1 and the sample mean of x2, we divide by the standard deviation, divided by the square root of n. And this gives us a t-statistic. Now, what if 2 samples were very close to each other? Well, then the numerator would be close to 0. So consider the fact that you have 2 classes that are almost the same. They take a test. They score, one scores an average of an 88, the other scores an average of an 88. We would say that those 2 groups were statistically the same. There was no difference between the groups. Let's assume that the 2 means were different. Let's say we had one class that had a mean of 100 and another class that had the mean of 80. Then the numerator would be large because that would be 20. And so long as our denominator was small, that would mean the t-statistic would be very large. But there's another case where the samples might be different. Let's consider the case where we have 2 samples that have the exact mean. Sample 1 has 500 as a mean, sample 2 has 500 as a mean. What if their variance was different? Now remember, the variance is related to the standard deviation, because the standard deviation is just the square root of the variance. And remember that if we have a wide variance, that means the data is spread quite widely around the mean, whereas a smaller variance, it's much closer to the mean. In this case, sample 1, which had an average of 500, actually has a standard deviation of 281.4. And the second one, as we can see the numbers are much closer to each other, has a sample deviation of 5.6. Could they really come from the same population? In other words, the curves, if you think intuitively, one would be a lot fatter and the other ones would be a lot thinner. Are they really from the same population, even though they had the same mean? If we look at this carefully, you'll see here on the graph, we have the green line basically shows us one mean, whereas the other one, which is much wider, is the black line, and that's the sample 2. The means are identical, but the variances, otherwise known as the standard deviation we're going to use, is different. And this means that the data comes from a different population. However, using our t-statistic, as we had done in the previous module, it would provide a result that says the 2 samples are the same. So this is a little bit of a problem. The first thing we want to do is we really would need to have equal variances, and this is one of the tests that we need to do. Now, in a previous module, we demonstrated that testing for equal variance is actually fairly simple. If the 2 variances were equal, then their ratio would be 1, and that's what this is showing here. Since we only have the sample variances, we will substitute these population variances that we see with our sample variances, and they should be equal to 1. Now, no two sample variances are going to be the same, so there's going to be a little bit plus or minus. But this ratio of the variance has been found to be distributed to an F distribution. So we can calculate the F statistic using previous procedures and see if the variances are equal. We calculate the F statistic, and then we look at the p-value. And our rule then comes into play. If the p-value is less than the confidence interval, we reject the null hypothesis that the variances are equal. The next slide will set up the hypothesis test. So here we have the same data set that we had before. I compute my F statistic, which is the sample variance of 1 over the sample variance of 2. And I end up with 25.51. Now, if we look up in the F table, or if we use a statistical tool such as Excel or R, we can actually get the F critical value, which is 2.21. Here we have the F statistic with a 0.05 significance level, and 18 degrees of freedom for one sample and 18 degrees of freedom for the second sample, which corresponds to n-1 number of observations in each sample. Each sample had 19, we subtract 1 and we get 18. Computing this in Excel or any other application would give us a p-value of less than 0.05, and we would reject the null hypothesis using the probability from the p-value. So we get the same result. So now we're going to take a look at ANOVA. Now, ANOVA is an acronym for analysis of variance, and it's used when we're comparing more than 2 groups. So before, with the t-test, we only compared 2 groups. ANOVA has similar assumptions to the t-test, that the data is normally distributed within each group, that the variance between the groups is equal or approximately equal, and that the observations are independent of each other. In ANOVA, just like the t-test, the dependent variable is a continuous variable. Things such as miles per gallon, class scores, or even total number of clicks in a day. The independent variable in ANOVA is going to be categorical: male, female, New York City, Los Angeles, Chicago, class 1, class 2, class 3. Now we have different terms for ANOVA. If we have one independent variable, we have a one-way ANOVA. If we have 2 independent variables, we'll have what's called a two-way ANOVA. If we have 3 independent variables, we'll have a 3-way ANOVA, and so forth and so forth. You'll rarely go beyond 3. Now, when we create a study for group comparisons, there are different ways that we can obtain the data. The 2 ways that we're going to obtain the data will be observational and an experimental design. In observational data, we have data that's obtained usually in the field or by some mechanism where we've collected the data via surveys or data that's available, such as economic data. And economic data is really a great example of observational data because we're collecting data on stocks, on economic values, and so forth. In experimental design, it's usually conducted in a lab, whereby a researcher can obtain the data, controlling for certain factors in order to remove confounding factors. So in other words, some business scholars will actually create an experiment in a lab using a computer auction, in which they will actually put students at certain terminals and give them certain controls, say in an auction. Some will have the ability to communicate with each other, some will not have an ability to communicate each other, and the test will occur to see if communication actually makes a difference. In these experimental designs, the researcher's trying to control for any external factors and any external biases as much as possible. Researchers will sometimes use alternative terms for independent and dependent variables. But independent variables can be known as factors and can contain 2 or more levels. So the factor for gender would have 2 levels of male and female. The factor for city might be something such as New York City, Los Angeles, and Chicago. Dependent variables are the variables of interest or response variables. So these are the terms that are associated with these types of designs.